So think about this for a second. How do you measure the exact number of photons in a beam of light without actually destroying them? It's a classic quantum paradox. I mean, in the everyday classical world, you count cars passing by just by looking at them, right? Simple. But in the quantum realm, it's a completely different ballgame. The very act of looking at a photon with a traditional detector usually absorbs it. You literally destroy the very thing you were trying to study. But what if the absence of information could actually tell us everything we need to know?
Welcome to this explainer. Today, we're basically playing the role of quantum detectives. We are going to break down this absolutely fascinating theoretical physics paper by Pegosov and his colleagues. They've modeled a major breakthrough using a single superconducting qubit, which is essentially an artificial atom on a microchip, to decode the hidden statistical properties of light. It's a super clever workaround. Okay, let's dive right into this.
Here is our roadmap for the investigation. 1. The wave-mixing phenomenon. 2. Enter nonclassical light. 3. The squeezed light mystery. 4. The single photon limit. And finally, 5. Decoding the missing peaks.
All right, part 1, the wave-mixing phenomenon, establishing our classical baseline.
Okay, so to spot a quantum anomaly, we first need to define the fundamental physical interaction at play here, which is wave mixing. It's a pretty well-known nonlinear optical phenomenon. Basically, when incoming light waves interact inside a nonlinear medium, which in our case is a single artificial atom or qubit, they generate entirely new output frequencies. And throughout this whole process, the total energy of the photons is perfectly conserved. Think of it kind of like a frequency blender. You put specific pitches in, and boom, you get new, mathematically related pitches out the other side. So here is our baseline. When the qubit is irradiated by two continuous classical coherent waves, we get this beautiful, perfectly symmetrical staircase of side peaks. Because classical light supplies a continuous flow of independent photons, the mixing creates this really robust, continuous flow of energy that generates waves at new frequencies in all directions. This symmetrical, plentiful structure, that's our control group. Keep this in mind. Moving to part 2, enter non-classical light, our quantum twist. Now, this is where the researchers introduce a major twist. What actually happens if we swap out one of those classical waves for non-classical light? Well, unlike classical coherent waves, which behave like a steady, highly predictable stream of independent photons, non-classical light plays by entirely different rules. It has highly complex photon statistics. It features these specific empty states, literally zero occupancies in certain energy levels, and incredibly strict quantum correlations between the photons. Because the inputs are so fundamentally different, the physicists hypothesized that the wave-mixing outputs on our single artificial atom would behave completely differently too. Which brings us to part 3. The squeezed light mystery, the case of the vanishing frequencies. Welcome to our first quantum crime scene. The researchers modeled what happens when you mix a standard classical drive with broadband squeezed light, which is essentially light generated by a specialized quantum amplifier. And just consider this bizarre result. Compared to our perfectly symmetrical baseline from earlier, entire frequencies have completely vanished. The whole spectrum is shifted, and specific peaks are just gone. It's as if certain frequencies have literally been erased from existence. So, the million-dollar question, why did they vanish? Well, squeezed light generated this way doesn't arrive as a continuous stream of single photons. It arrives in strictly correlated pairs. It's like a quantum buddy system. Now, when wave mixing occurs, it relies on multiphoton scattering. But because the squeezed light only offers photons in pairs, any multiphoton process that would require an odd number of photons from this non-classical mode is, well, physically impossible. Since those specific interactions just can't happen, the corresponding frequency peaks simply cannot be generated. Makes sense, right? Let's look at part 4, the single photon limit, an extreme quantum case. Now, instead of squeezed light, let's introduce a periodically excited quantum superposition of 0 and 1 photons. Basically, a single photon source. And the resulting emission spectrum is incredibly sparse. I mean, it is severely restricted. We don't just have a few missing peaks here. We have almost no side peaks at all. The entire spectrum is limited to just 3 vertical lines. The mechanism behind this is absolutely fascinating. Think of this non-classical light source as the world's strictest bouncer at an exclusive club. It physically allows a maximum of either 0 or exactly 1 photon to exist at any given time in that mode. Because higher-order multiphoton scattering requires multiple photons to mix simultaneously, those complex higher-order interactions are completely starved of the photons they need. You just can't mix what isn't there. The only side peak that can actually form is the one created by two photons from the classical wave mixing with the single available photon from the nonclassical wave. Finally, Part 5, decoding the missing peaks and discovering the quantum ruler. Let's bring all these clues together because it builds a super compelling picture. When we use two classical waves with a continuous flow, the spectrum is perfectly symmetrical and all peaks are present. Mix classical with squeezed light, where those photons arrive in correlated pairs, suddenly the odd peaks are completely absent. And finally, mix classical with a single photon source, where you have a strict maximum of one photon at a time. The spectrum is severely limited to just 3 peaks. You can see precisely how the nature of the photon delivery dictates the final visual output of the spectrum. And this right here leads us to the researchers' massive aha moment. The absence of these peaks isn't a failure to generate light, not at all. The missing peaks are actually a highly precise mathematical ruler. By mixing an unknown light source with a classical drive on a single artificial atom, you can look at the resulting wave-mixing spectrum. By analyzing exactly which peaks are missing, you can reverse engineer the quantum statistical properties of that light. It literally allows you to probe the exact photon statistics without ever having to run them into a destructive detector. This explainer really highlights the incredible potential of superconducting quantum circuits. I mean, we are moving way past just building qubits. We are using them as highly sensitive, non-destructive tools to interrogate the fundamental nature of light itself. With this theoretical model acting as a brand new quantum ruler, what future breakthroughs await us in on-chip quantum information processing? If we can measure the unmeasurable simply by analyzing what's missing, the possibilities for quantum sensing are absolutely boundless. Keep questioning the physical world around you, and hey, thanks for learning with me today.